Hello, everyone. Welcome to my talk. My name is Tao Xu. I'm a postdoc at the University of Oklahoma. Today, I'm going to talk about probing new physics with primordial black holes. The talk is based on working in collaboration with Gauss Debagashi, Jihan Chang, Stephen Clark, Pascal Dada, and Yuxin Cai. Let me first introduce the idea of primordial black holes. Black holes are interesting objects in the series of gravity and also in a series of the fundamental particle physics. We know black holes can form from the collapse of stars, and these astrophysics black holes can be observed with gravitational wave signal and electromagnetic signals. In the meantime, black holes can also form in the early universe when the environment is very dense, and these black holes are primordial black holes. Primordial black holes can exist in a wide mass range, and this depends on their formation mechanism. In this talk, I'll focus on the black hole mass around 10 to 15 grams. This is the asteroid-mass window for primordial black holes. In general, the origin of primordial black holes are related to interesting cosmological models, and primordial black holes can become heavy dark matter candidates if they are stable. Hawking temperature is higher for light primordial black holes, and this means their Hawking radiation process is more active. And this leads to interesting phenomenology of particle production with Hawking radiation process. For asteroid-mass black holes, their lifetime is longer than the age of the universe. We can calculate the lifetime of primordial black hole, and we'll see that for black hole mass larger than 10 to 15 grams, it can be stable today and become dark matter candidates. In this figure, I'm showing the fraction of dark matter made of primordial black holes as a function of mass of primordial black hole. Different color regions are the exclusion for PBH using different probing signals. And with this region labeled as A, B, C, and D, they still allowed a large black hole abundance to be dark matter. And for asteroid-mass primordial black holes, they are in the left side of this figure. And you will see currently the strongly constraint on asteroid-mass primordial black hole is from their Hawking evaporation. The Hawking radiation tells that the particle can be produced by the tidal force around the black hole horizon, and the particle production spectrum is close to black body shape. The Hawking temperature of the primordial black hole is inversely proportional to the black hole mass. That means for a primordial black hole of 10 to 15 grams, their Hawking temperature can be as high as 10 MeV. If asteroid-mass primordial black holes are evaporating at MeV energy, we can try to look for such kind of signal. For example, if primordial black holes are generate gamma rays, you can use the indirect detection search look for them. The gamma rays coming from primordial black hole can get different contributions. First, there will be photons directly produced by the Hawking radiation process. And the primordial black hole can also generate other charged stem model particles, and these charged particles will generate photons with the final state radiation process. In the end, pions can be produced by a primordial black hole, and the pions will decay to photons. We can add up all these contributions to get the total gamma reflex curve in this blue color. So around the Hawking temperature peak at the high energy, the most contribution are coming from photons directly produced by the primordial black hole. And in the low energy part, the most contribution are from the final state radiation. Assume every black hole generates photons at this flux. You can use the non-observation of additional photons to put a constraint on FPBH. So using existing data from the gamma research from the galaxy center, these authors put a constraint on FPBH in the asteroid mass window. And you can see for black hole mass lighter than 10 to 17 grams, they cannot make up 100% dark matter, assuming a monochromatic mass distribution. And the bonds go stronger for light black hole mass because the Hawking radiation power is more efficient for light primordial black holes. In the future, we'll have more gamma research and MeV energy. And if we can improve our sensitivity to MeV gamma ray signal from 0.1 MeV to 100 MeV, this energy range can be translated to the Hawking temperature of primordial black hole from 10 to 14 grams and to 10 to 17 grams. So for asteroid mass black holes, our sensitivity will be much better in the future with these new experiments. Gamma ray is not the only signal channel to probe primordial black holes. In a recent study, we look at the primordial black holes formed in the early universe from the collapse of the density fluctuations. We find that the curvature perturbation that generates the primordial black holes will also predict a strong gravitational wave. And if we observe the gamma ray signal and the gravitational signal today, we'll be able to use multi-messenger signal to get more information from the primordial black holes. In these two panels, we're showing the signal strength, assuming a different curvature perturbation model. And on the left panel, we show the range of the gamma ray signal can be higher than the future E-astrogan experiment. And on the right side, we show the corresponding gravitational wave signal will also be higher than different proposed gravitational wave observations. Following this idea, we use different kinds of signal to perform a pyramid fit to the curvature perturbation spectrum, and we find there's an interesting correlation between gravitational wave signals and gamma ray signals. For example, using the gamma ray signal with the E-astrogan experiment, we'll be able to constrain the pyramid space of this curvature perturbation within the green contour. And for the gravitational wave signal, the constraint of the pyramid space well within this blue contour. They show a different correlations, and the overlapped region is close to the true model, which is showed as the black star. And in the future, the BBL experiment will be very sensitive to the gravitational signal and will be able to put a much better constraint in this shown in this red contour. So this tells us the multi-messenger observation can both test the abundance of primordial black hole dark matter and also tell us about their cosmic origin. If we can measure primordial black holes more precisely, we can use them to test new physics theories. If we look at the Hawking radiation process more carefully, the particle production rate is written here, and you can see the Hawking radiation produces particle via gravity, and it only depends on degree of freedom, Gi, not other coupling constant in particle interactions. This means Hawking radiation is another channel to produce new particles that exist in the particle spectrum, even if their non-gravitational interaction are feeble. Also, the particle mass should be kinetically allowed by this relation. The particle mass should not be much larger than the Hawking temperature of primordial black hole. Since asteroid-mass primordial black holes are evaporating at MeV, they can efficiently produce any beyond star model particles with their mass at MeV or smaller. Therefore, we can ask, can we use primordial black holes as a particle factory and generate new particles with primordial black holes and test their existence? The answer is yes, and in the rest of this talk, I'll use axion-like particle as an example to illustrate this idea. So axions are originally proposed to solve the strong CP problem in QCD, and the axion-like particles is a generalization of the phenomenology of QCD axions. We can write down the Lagrangian of the axion-like particle, and it's a pseudo-scalar particle coupled to photons. Then a primordial black hole can generate the axion-like particle as well with the Hawking radiation process. And after the production, axion-like particle will decay to 2 photons. Therefore, the axion-like particle can modify the gamma ray spectrum. Let's calculate the modification. So the production of axion-like particle will not change the production of other star model particles. That means the 3 contribution from primary photon, final state radiation, and pion decay will remain the same. And we can add the new phase contribution from the axion-like particle decay shown in the second line. And the overall contribution will get as a modified gamma ray spectrum. So here I'm showing the gamma ray spectrum based on different assumption of the serial model. The standard model only case is shown in this purple color, and the red, green, and the blue curves show the case when we add an axion-like particle into the spectrum and let the axion-like particle decay to 2 photons. You can see that the red, green, and blue curves are higher than the purple curve because there are additional photons coming from the axion-like particles. And because the axion-like particle generate photons with a decay process, the location of these additional photons are different from the primary photon peak, and they generate a double peak feature in the gamma ray spectrum. So this is the new signal in the gamma ray spectrum that we can look for in an indirect detection search. We propose to look for the signal from the galaxy center. Assume primordial black holes make a fraction of dark matter, and they're in the galaxy center, generating a lot of particles with the Hawking radiation process. And the full gamma reflex will be observed by the asteroid experiments in the future. We can use the gamma signal to test the serial model. There are 2 serial models we want to distinguish. The first one is standard model. Assume there are only standard model particles exist and be produced by primordial black hole. And the axion-like particle is kind of a new physics model that assumes standard model particle and axion-like particle are both produced by the primordial black hole. So here is the gamma ray spectrum assuming a fixed black hole mass of 10 to 50 gram, a fixed fraction of 10 to minus 8. And you can see the different color curve can be higher than the future sensitivity of the asteroid experiments. And depending on what is the number of photons that can be observed in the entry window of the asteroid observation, we'll be able to perform a spectral analysis with the number of photons in each energy beam and get the information of the Hawking radiation spectrum. So what can we learn from that? First, the primordial black hole constraint we set with the gamma research, it depends on the serial assumptions of the Hawking radiation spectrum. So in the previous sensitivity set by the gamma research, they assume only standard model particles are produced and contribute to the photons. So the constraint on FPBH, shown in this dashed gray curve, is by comparing the axis of photon coming from standard model particle versus astrophysics background. But if we change the serial assumption and add axion-like particles with their gamma reflex contribution, there will be more photons for a fixed primordial black hole model. And we need to compare the standard model contribution plus the axion-like particle contribution versus the astrophysics background. This will give us a stronger constraint on FPBH if axion-like particle exists. The update constraint with the assumption of axion-like particle is shown in this the color dashed curve, and you can see the bound is lower than the dashed gray curve, which assumes standard model only. Also, we can not only discover primordial black hole, we can try to identify the existence of axion-like particle. So if FPBH is larger, then we'll be able to see more photons and reconstruct a Hawking radiation spectrum. That will give us enough statistics to distinguish the axion-like particle model from the standard model. So the result is shown in these solid color curves. If FPBH is higher than these solid color curves, we'll be able to tell the existence of axion-like particle with the shape of the gamma ray spectrum. In the end, let me show the axion pyramid space that can be probed with primordial black holes. With Asteroid-mass primordial black holes, we can test the pyramid region for MEV axions. By different assumption of the primordial black hole mass and primordial black hole abundance, we can test the different regions in the GA gamma coupling versus MA mass plane. So if we choose the primordial black hole mass to be smallest one, the Hawking temperature is higher, and it can extend to further right side to test the heavier axion-like particle. And the right edge is determined by the relation of the axion mass versus the Hawking temperature. So as long as the axion is not too heavier than the Hawking temperature, we can use method to test them. And the lower edge is determined by the lifetime of axion particle. This is because we're looking for gamma ray signals from axion decay originating from the galaxy center. So we require the axion-like particle to decay before reaching Earth. So this is the region we can test with the primordial black holes. And this can be complementary to existing axion-like particle constraint that is shown in the background with the green color. And this can open up the pyramid space that are not tested with the existing method. In the end, let me summarize my talk. So for asteroid-mass primordial black holes can make up a fraction of dark matter, and the MEV gamma ray signal from Hawking radiation process can be used to probe primordial black holes. Multi-messenger observations with gravitational wave signal provide us with more information about these primordial black holes. Then we can look at the Hawking radiation process more carefully. Hawking radiation is via gravity. That means primordial black holes can produce new particles efficiently, as long as the new particles are not too heavier than the Hawking temperature. And then we use axion-like particle to show that Hawking radiation spectrum analysis can be used to detect the new particle produced by primordial black holes. Then, if we do detect Hawking radiation signal in the future, we can use the radiation spectrum to probe both primordial black holes and also beyond stellar model particle degree of freedom that could have been produced by the Hawking radiation process already. Thank you.